you very much to the organizers for having me here. So I'm going to be speaking on SLE and LQG, and if I sound really poorly, so if I fall asleep during my talk, please wake me up. Okay, so what is SLE? So this is the outline for what we're going to go through today in the first lecture. We're going to discuss what SLE is, and state some results that you can get about SLE and conformal field theories. And then we'll jump into Liouville quantum gravity, starting with the definition of the Gaussian free field and Gaussian mass field chaos. Okay. So what is SLE? So it's a random non-self-crossing curve. So it has here you've got 3 simulations of SLE with different roughness parameters kappa. So this is SLE3. The parameter kappa is less than or equal to 4, so you're going to get a simple curve. And kappa is between 4 and 8. Strictly, you're going to get a curve that is allowed to hit itself but not cross itself. So, a cartoon picture maybe. So the curve will bounce off of itself and off of the boundary, but it will never cross itself. Okay, and it's a fractal, so it hits at a countable sort of. Not a countable self, it's an uncountable self. Sorry. Yeah. So the fact that the roughness is increasing as kappa increases, one way to measure that is in the Hausdorff dimension. And so all of these curves have fractal dimension bigger than 1. They're rough, right? They're not a straight line. And it's increasing until they become space filling. And that's the kappa at least 8 regime. Okay, so in this picture, the time parameterization is given by the color. So you start with the red color, and you move on to orange, yellow, because I mean you can't really plot a space filling curve without something like that. Okay.
So last question. How strong is the condition of having a simply connected domain?
Yeah, that's a really good question. I believe I have a talk later today about multiply connected domains. Yeah, but there are lots of different variants for SLE, and the simplest one is caudal, but you can define SLE loops and SLE on non-simply connected domains as well. Yeah. Okay. So I guess I'm just going to zoom into the pictures here. So this is a simple regime for SLE. So these curves are not going to hit themselves. It does look like they get very close to touching themselves, but they will not actually self-intersect. So this, I should have said this earlier, the simply connected domain is the upper half plane, and this curve is joining 2 boundary points, the origin and the point at infinity. Okay. So next is this SLE with kappa is equal to 6 simulation. So this is some kind of discretized simulation, so it doesn't have the actual properties of SLE. You really do want to see this curve hit the boundary and hit itself. Okay. Finally, this zoomed in picture for the SLE with kappa bigger than 8. I guess it's going from red backwards in the rainbow, I guess, from red and pink to purple. It goes up this region, then comes back this way, and so on and so forth. Okay, so these are really cool curves and pretty simulations, but why do we care about these things? The main motivation is that these random curves describe scaling limits in critical statistical physics models. So the first example where this was shown is in the example of site percolation on the triangular lattice. Okay, so drawn here these hexagons, and now what we're going to do, well, you're going to color the left boundary one color, and the right boundary a different color. And for every hexagon inside, which is not a boundary hexagon, you flip a coin. This is critical percolation, so your coin is fair, and with probability 1/2 you color it blue, with probability 1/2 you color it yellow. So that's going to give you this configuration over here, and you can see that there's a special interface between the yellow and blue colors. So you start at the origin, and you just trace this interface. You can already see that in this discrete model, the curve gets very close to hitting itself, it's an interface, so of course it will not actually hit itself in the discrete. But when you set your mesh size to 0, this is going to converge to SLE with kappa is equal to 6, which is in the self-hitting regime. So this is the first example where it's shown that a critical statistical physics model interface satisfies some kind of conformal invariance property that it converted to SLE. Okay.
Is there an analog of K in the discrete models?
Or kappa.
Of kappa,
Yeah. Yeah, you can define various models for which kappa is a continuous parameter, like your FK random cluster model or ON loop model. We'll say a bit more about that later. Yeah. Are there any other questions? No, then let's move on to another example. So here we have a critical Ising model on the square lattice. And we have these evolution boundary conditions. So let's say we fix the left and the top boundaries to be plus spins, and the bottom and the right boundaries to be minus spins. And we sample one of these critical temperature Ising models, like what Marlon was talking about yesterday. And you can do the same story. You look at the interface between the two colors, it's going to give you this discrete curve. And as you send your mesh size to 0, it's going to converge to SLE with kappa is equal to 3. Okay, so this is a simple curve regime. You should get a simple interface in the scaling limit. Okay.
Okay, I have another question.
Yeah.
Is there a reason, from given a model, can you kind of see what the kappa value should be? Is there a reason that one is kappa is 6 and one is kappa equal to 3? Is there something intrinsic in the model that you can?
That's an excellent question. In general, there's not a single thing that you can just do, but there are different properties that will help you identify the value of kappa. So, for example, over here, this curve satisfies locality in the sense that suppose I have two different domains. Maybe I've got one. Draw a different picture here. So maybe I've got a domain that looks like this, and a domain that mostly looks the same, but it has a little distortion. And let's say I explore my SLE6 curve until some stopping time. If I condition on the event that my curve is stopped before it sees a difference in the shapes of the domains, so it stays inside this region, for example, then the laws of the SLE6 here and the SLE6 here are the same. And this is a property that's natural in the discrete because, well, every hexagon is colored independently of every other hexagon. So if I distort my region over here, the interface is not going to see that. So this locality property, you can check that the only SLE satisfying locality is kappa is equal to 6. In general, you need to do something different for every model, but there are ways to identify the kappa values. Are there any other questions? Okay. So the last example is going to be this uniform spanning tree example. So we're on the square lattice, and we have some vector linear region. We have one boundary arc, which is shown in black, and then this is a dual boundary arc. So the red dots are the dual vertices. Each face gets a red point. And so what you're going to do now is you're going to sample uniformly among the set of spanning trees. So shown here in black is an example of a spanning tree. There are finitely many ways to draw a spanning tree, and we're going to choose one of them uniformly at random. Now, given this configuration, we can get a curve as follows. We start at one endpoint of the wired black boundary arc. We put our hand on the wall, and we just trace it like we're trying to escape the labyrinth. You can convince yourself that when you do that, we're actually going to visit every single square in this picture before exiting. It's the least efficient way to escape the labyrinth. Okay, so this orange discrete curve is discrete space filling. And it turns out that when you send your mesh size to 0, this random curve is going to converge to SLE with kappa is equal to 8. Okay, so we've seen 3 different examples of discrete models with 3 scaling limits, which are SLE in the 3 different regimes we talked about: simple curves, self-fitting curve, and space-filling curve. Okay, so this is the main reason why people started investigating these curves, because they describe the scaling limits of statistical physics interfaces. So one more example. You will not win $1 million if you do this, but you'll self-actualize. This will give you joy. So we're going to take a simply connected lattice domain with 2 boundary points. So for simplicity, maybe an n by n grid. And you mark these 2 boundary points. Now we're going to consider the set of all possible curves from one boundary point to the other, which are simple curves, so they do not repeat vertices. This is as n tends to infinity, this is a huge set, but it's a finite set, so you can sample an element from it uniformly at random. This model of random curves is called the self-avoiding walk. So one of the biggest open problems in the field is to show that the self-avoiding walk converges to SLE with the kappa value 8/3. Okay.
Why is the value 8/3 believed to be the one?
Yeah, the value is 8/3 because this kappa value satisfies the restriction property, meaning that if you take, let's recycle this picture here. So let's say I've got 2 domains, and this domain is a subset of this domain. And suppose I sample SLE 8/3 here between the 2 boundary points, and I restrict to the event that that the curve stays in the domain D. So let's say this is D, and this is a bigger domain D prime. And if we take the SLE 8/3 curve conditioned on it staying inside D, then conditioned on that, the curve is going to have the law of SLE 8/3 inside this region. This is a restriction property. The curve in the bigger domain, conditioned to stay in the smaller domain, has the law of the curve in the smaller domain. Yeah, so what you can do is check that only one kappa value satisfies this property, and that's 8/3. Okay. Cool. Are there any other questions? Okay. So now let's discuss some properties that we expect of scaling limits of interfaces at criticality. We're going to use these properties to motivate the definition of SLE. Okay, so we're going to write SLE prime to denote the scaling limit of a critical interface. When you send a mesh size to 0, the physics answer is that first of all, these curves are going to be conformally invariant in law. So conformal invariance means that a conformal map is a holomorphic bijection between 2 domains. And what it does is it preserves angles. So if you take a conformal map, a small square is going to look like a small square under the map F. So the conformal invariance property says that if you have SLE prime in one domain, and you map into a different domain using the conformal map, then the resulting curve you get in the right domain should also have the law of SLE prime. Okay, so this is coming from some kind of fancy physics argument, which I'm not going to go through here.
Yes, Ante kind of explained it.
Yeah, right. Okay, so this is the first property, this conformal invariance in law. And the second property is the domain Markov property. This one is easier to see. So the story is, if you run your curve until some stopping time, and you ask, what is the conditional law of the rest of the curve? Well, this conditional law is going to be an SLE prime curve inside this simply connected domain, where you have your original domain and you cut the slit in it. So now you've got 2 boundary arcs on the left and on the right of the curve. And the law of the remaining of the curve is just SLE prime inside this domain. So the reason why this property is expected is because in all of these models, suppose that I've explored this interface for some amount of time, then what do I know? All I know is the colors of the neighbors of this curve until this point. And once I stop, I haven't seen any of the other colors yet. I can just sample them with independent coin tosses, etc. So the rest of it is still going to be an independent, it's still going to be a percolation interface in the slit domain. Convince yourself that the same kind of properties hold for the Ising model and for the uniform spanning tree. Okay? So the second property is generally easy to guess when you start with a critical lattice model. Okay. So you've got these two properties of random curve, and the goal is to identify every possible random curve satisfying these two properties. Okay. Once we've done that, then that gives us all the candidates, all the possible candidates for the scaling limits of these lattice models. And this is the part where I kind of do a rug pull, I guess. So I'm not actually going to define SLE, because it's not going to be, the definition is not going to be useful for the rest of this mini course. But the point is just that you can define SLE using a certain stochastic differential equation, and inside this differential equation shows up a Brownian motion term. And the reason the Brownian motion shows up is because Brownian motion is the only random continuous process satisfying a scale invariance property, meaning if you dilate the random process by some factor, then this up to time change is the same as in law as the original process, and also the strong Markov property. And we need these two properties to hold because of the two corresponding properties that we have for the SLE curve. So the SLE curve satisfies conformal invariance and domain Markov property. These two properties translate the statements about this so-called driving function. So you know it's Brownian motion. So this is where the parameter kappa comes from. Brownian motion is the only process satisfying these two properties up to rescaling. So you can replace Brownian motion with root kappa times Brownian motion and still have this property.
What is Z?
Yeah, what is this equation?
No, Z.
Z. Yeah. Yeah, I wasn't planning to discuss this SDE stuff because I'm not going to use it again later
You
on.
can make a small figure.
I could make a small figure. So it's something like this. So we're going to draw this random curve up until time t. And what we're going to do is we're going to define this random conformal map, GT. So this shaded region in the complement of the curve up until time t, this is essentially called the domain with two boundary points. One is a curve tip, the other is a point at infinity. So by the Riemann uniformization theorem, there's a unique map. You can find a conformal map from this shaded region to the upper half plane. And we're going to ask for the map GT to satisfy the following property. So first of all, this map sends the point at infinity to the point at infinity. And second, hoping I wrote this down correctly. So the statement is saying something like, the map looks like the identity near the point at infinity, and also the first order correction term is going to look like 2t over z. Yeah. So you can define a unique conformal map. Given the curve up until time t, you define this gt. It's a deterministic function of the curve, but it's a random function because the curve is random. And this random function satisfies this differential equation shown over there.
So the z is in the upper half plane
Yes.
minus curve, right?
Exactly, yeah. So you have a point z in the upper half plane. It gets mapped to some point. It gets mapped to some point still in the upper half plane. You're kind of unzipping this curve. The conformal map is pulling everything down. So this point kind of comes down and becomes this point GTZ. And the question is, how is this point moving in the upper half plane over time? And the answer is it's moving according to this differential equation. Okay, so every single point Z is evolving with the same down in motion according to this differential equation. So as a process, as they cut further along the curve, every point is being pulled downwards towards the origin according to that differential equation. Okay, I don't know if that was too low, but yeah. So that's how you can rigorously define SLE as a family of random conformal maps. It takes some additional work to show you actually get a curve, but I'm not going to go into that. Are there any questions? Okay, so I wasn't planning on discussing this because I'm hoping to discuss a different approach to SLE. But loosely speaking, and anyone in the audience should correct me if I'm missing something which you call a different approach here. But there are roughly 3 different ways to tackle SLE problems. The first is directly using the stochastic differential equation that I wrote down earlier. And in this approach, you're going to be using martingales and computing things using Edo calculus. So for example, this locality property I mentioned for SLE6, you would check that this is true for kappa is equal to 6 using this definition by checking something as you just write out some stochastic differential equations and do a thing. Okay, so that's the first approach. The second approach is some kind of coupling of the random curve with a random generalized function called the Gaussian free field. I'll say more about this object later. And the third approach is using something called Liouville quantum gravity, which is a model for random 2D surfaces. So what we're going to do in the course of these 4 lectures is to discuss how this third approach works and how it allows us to compute things that were predicted from the physics literature. Okay, are there any questions? Yeah, okay. So that was my very brief introduction to SLE. And next I'm going to give 2 statements which connect SLE to CFT. So the first story comes from a loop variant of SLE. So for SLE, you typically have something like Dobrushin boundary conditions for a discrete model, and you trace the interface. But you can instead have models where you, for example, have the Ising model with just plus spins on the boundary, and when you sample the configuration, you're going to get something that looks like this. Right? So we're going to have the same story where we look at these interfaces between the 2 spins, and that's going to give us a set of discrete random loops. And when you set the mesh size to 0, it turns out that you can take a scaling limit of all of these loops simultaneously. And what you're going to get is a random collection of loops. These loops are, they're going to look locally like SLE curves. So there's a family kappa for the conformal loop ensemble. They're going to be disjoint loops when kappa is less than or equal to 4. They're going to be self-hitting loops, and they'll hit each other as well, and the domain boundary when kappa is between 4 and 8. So in short, the conformal loop ensemble is a random collection of SLE loops that don't cross each other and arises from the scaling limit story. Okay, so this is an object you can canonically define in simply connected domains. So for the disk and for the Riemann sphere. Okay, so similar to SLE, this object is conformally invariant in law, meaning if I start with a conformal loop ensemble, apply a conformal automorphism to the unit disk, that gives me a new collection of loops, and this new collection of loops also has a law of the conformal loop ensemble.
Why is kappa need to be inferred?
Yeah, that's a really good question. How do I answer this?
What was the question?
The question is just why is the kappa value in this range? I guess you can write down, so the construction is done in terms of SLE, and it only works for this parameter range. For kappa less than or equal to 8/3, you just cannot have any loop ensemble which satisfies something like a domain Markov property and a conformal invariance statement. This was shown by Sheffield and Werner, who, for a collection of simple random loops with domain Markov property and conformal invariance, it has to be CLE with kappa between 8/3 and 4. And then for kappa between 4 and 4, once kappa is bigger than or equal to 8, you get these space-filling curves. You can try and construct some kind of conformally invariant random loops, but offhand I don't know a reference for this kind of story. It's an important open problem to show some kind of characterization statement for kappa between 4 and 8. So, can you write down some notion of the domain Markov property and the conformal invariance that characterize these random loops? Okay, so that was a good question, and I maybe went into too much detail there, but yeah, these numbers are not arbitrary. Are there any other questions? Okay, so you have these random loops which look like SLE. Here's a simulation for kappa is equal to 4. So it turns out if you just draw every single loop, you're just going to color the whole circle in like completely black, right? Because these loops are nested like this, and their union is going to be dense inside the disk. So what I've drawn, what David Wilson has drawn here is just the outermost loops of CLE on the unit disk. So each of these white regions, its boundary is going to be one of these CLE loops. So this corresponds to one loop, this corresponds to another loop, and so on and so forth. So the story I want to tell first has to do with the 3-point nesting function for CLE on the sphere. So we're not on the disk anymore, we're in the sphere, we have this full collection of nested loops. And we're going to fix 3 points, so they're shown in red, green, and blue. And I've colored in red the set of all loops in this toy picture, which separate the red point from the other 2 points. Okay, so the complement of each red loop has 2 components. One component contains red, the other component contains blue and green. So I want to write down some kind of notion of a exponential moment for the number of loops that separate each point from the other 2 points. But this doesn't make sense because there's infinitely many loops. So I've only drawn 3 red loops, but there should be infinitely many really small loops as you get closer and closer to the red point. Okay. So we're going to use some kind of cutoff that x epsilon z1 be the number of red loops, which are at distance at least epsilon from the red point. Okay. So we're just cutting off this infinity of loops by only looking at the large loops. So what we want to do now is compute the joint, some kind of joint function of these 3 loop counts. I'm not going to state the exact version, but we're going to let n1, n2, n3 be 3 parameters, And the quantity we care about is this exponential of ni over n to the number of loops separating zi from the other 2 points. So as epsilon tends to 0, these loop counts are going to blow up. So the epsilon zi's are going to become larger and larger. And so we need to put some kind of renormalization factor, which is going to be epsilon to some power. Okay, this power could be positive or negative, depending on whether this ratio is bigger than 1 or less than 1, respectively. So you can write down this renormalized quantity, set epsilon to 0, and what we can show is that this is going to converge to some kind of limit as epsilon tends to 0, and this limit satisfies is of the following form. The dependence on the locations of your 3 points z1, z2, and z3 is trivial in the sense that it's explicitly written down by this product over here. So this is the same story that we saw in Anti's talk yesterday, where these 3-point correlation functions, you don't really care where the 3 points are. The dependence on the location of the 3 points is explicit. And all the interesting information is contained in the 3 factor here. I guess post factor, the way I wrote it down.
So sometimes ends are related to z's, right?
I guess the ends, yeah, sure. So we've got 3 parameters and 1 and 2.
You have like some weights. But then I'm very confused on what that is, as opposed to the end that depends on kappa.
Yeah. So I'll say more about this later, but this collection of loops, you can think of it as coming from some ON loop model, a random model with a parameter n, and we're modifying the model by changing the weights of loops which separate 1 point from the other 2 points. Yeah.
Is it like you want to detect those, so if you modify the weights, it's kind of showing it?
Yeah, exactly. Yeah, that's right. Cool. So we're going to write down some kind of reparameterization. So we started with these ni weights. We wrote down something in terms of delta I instead. We reparameterize one more time. I don't state the exact reparameterization. And you define this 3-point function, which we call R nes kappa. It's just going to be this 3-point function we had before with some kind of normalization in the denominator. Okay, and the theorem statement is that this nesting function of the conformal loop ensemble is exactly going to agree with the imaginary DOZZ formula that arises in conformal field theory. Okay, I'll say more about this imaginary DOZZ formula on the next slide. So this statement that we showed gives a mathematical proof of something that was done in physics in 2015. What the physicists did is they used some kind of numerical methods called the transfer matrix method to do computations for discrete loop models. Specifically, they take the ON loop model, meaning, let me write something down. So ON loop model, let's see if I can get it right. So omega is going to be a collection of loops in the lattice. For simplicity, let's just stick with the disk. And a loop is going to just be a path that is closed. So this is one loop. You can join another loop like this. And we're going to ask for these configurations of disjoint loops. Okay. Yeah, so omega is going to be this collection of disjoint loops. And let's say we write this as the total length of loops. And L is the number of loops. Then the ON loop model assigns to such a configuration the following weight. There's some parameters x and n. This is the same n as before, and the number of loops, I think, and x is the total length of the loops. Okay, so we're weighting each configuration by the number of loops, so n to that number. and X are the total length of all the loops. This is called the ON loop model. If you choose this correctly, then you choose this to be critical in some way, then let me rephrase. You choose X correctly, and what you get is the ON loop model. So what the physicists did is they looked at this ON loop model on the discrete lattice. They assigned different weights N1, N2, N3 to loops separating one point from the other two marked points. And then they computed the nesting function. So they computed this quantity. There they don't have a discretization because it's already in the discrete. Xi is just a total number of loops separating point I from the other 2 points. Okay, so this is, let's see. Yeah, so we proved this formula that they had conjectured and given this strong numerical evidence for using these simulations via the lattice, via the transfer matrix method. Okay, so how does this connect to CFT? Well, it's got to do with this imaginary DOZZ formula. I'll state what the formula is, but before that, I'll just talk about this stuff down here. So the imaginary DOZZ formula is a formula that was introduced in physics in the context of being a candidate structure constant for conformal field theories with central charge less than or equal to 1. So if you've heard of the minimal models conformal field theories, this imaginary DOZZ formula is some kind of a natural extension of the structure constants of minimal models to continuous varying parameters. Minimal models take central charges in some countable set of values, and the possible insertion weights are also coming from some discrete set, and you can kind of generalize everything using this imaginary DOZZ formula. So what is a DOZZ formula? It's going to be this expression on the top where, which is in terms of this special function called the double epsilon function over here. So the double epsilon function is defined in terms of this integral when your parameter z has a real part between 0 and q. Q is going to be root kappa over 2 plus 2 root kappa. So in this regime, this integral converges and defines this function, which turns out to be holomorphic on the plane, meromorphic on the plane, so you can just extend to the whole plane. So this is a really nasty formula overall, right? Because it involves all these special functions, but these things are explicit, they are computable. You can just, if I ask you for the value of the imaginary DOZZ formula, you can just kind of compute what it is. Yeah.
Is A just a constant? Or?
Yeah, sorry, I dropped that when I was making the slides. A is going to be some explicit function of alpha 1, alpha 2, alpha 3, but a simple function, something like a rational function, I think. Yeah. Okay, I don't necessarily want to dwell on this nasty formula, but the point is these conjectures come from conformal field theory, and these numbers are important because they're the structure constants or 3-point correlation functions of conformal field theories with central charge less than or equal to 1.
You go back to the formula theorem before, and here you have the formula in terms of B, then because the correspondence between kappa and square root of kappa over 2. So is there an explanation why, I mean, it could be maybe kappa and kappa on both sides, but it's kappa and square root of kappa over 2. Can you see this simply from the next slide in the formula and the imaginary imaginary DOZZ formula, or is there any other intuitive reason?
That's a good question. I guess you're asking like why you have this root kappa over 2 as the B value here.
Yeah.
I don't have a very good answer for this question. I will say though that there is this duality that is evident here, where this Q value is B plus B inverse. So like if you have Q is B plus B inverse, and B is root kappa over 2, And then this is somehow equal to the value, to something like this. So somehow it turns out that it's natural to have SLE kappa and SLE kappa prime in the same setting, where kappa and kappa prime satisfy this relationship.
Maybe one way to say it is the central charge is the same.
Yeah.
And these loop models have a central charge that you naturally couple with the Liouville. So.
Yeah. Yeah, exactly.
I just want to make a comment. So the central charge is 1 minus 6q squared, right?
This is not q squared. This is this minus is correct.
Yeah. And the other thing is, that the Epsilon function can also be written in terms of gamma functions if you don't like the polynomial. So it's like gamma functions are kind of fundamental in CFT, so it's not really scary.
Okay.
It's
Then
not
you
scary,
can write
but-
this double epsilon function in terms of gamma functions.
Yeah.
It's just longer than.
Yeah, I guess so. Yeah. Yeah, let's chat more about it later.
Yeah.
Okay. Are there any other questions? Okay. Okay. The second application I want to mention is more classical from the math perspectives. So we're looking at critical site percolation once again. We're on the whole plane, and every hexagon on the plane is colored either red or white, and we're going to have the mesh size be delta. So the size of each of these cells is going to be order of magnitude is delta. Okay, and now we're going to look at the probability that 3 points lie in the same cluster. Right? So, for example, the 3 blue points shown over there, they all lie in red hexagons, but more strongly. You can find paths between each pair such that you stay solely within the red regions. Okay, so they lie in the same red component. So this is an event that depends on the probability depends on the mesh size. Right? When you send delta becoming smaller and smaller, intuitively it becomes harder and harder for your 3 points to be connected. And so if you're going to define some kind of limit when your mesh size tends to 0, you must put some kind of renormalization factor in front. And that's exactly what is done here. So the limit that's chosen is you're going to look at the event that your point at the origin is connected to the unit circle on this size delta mesh. Roughly speaking, this is something like a probability that the point 0 is connected to some macroscopic cluster. And if you have n different points which need to be connected to the macroscopic cluster, namely the single cluster containing all of them, this is the correct scaling factor to put in front. Okay, so we'll see in a second that this exact choice doesn't really matter. Okay, so we define this connectivity constant for each choice of delta. We can define a scaling limit as delta tends to 0. Now I claim that the quantity that we really care about is this one over here, where you take this limiting connectivity for 3 points z1, z2, z3, and you divide by this product of the z1, z2, z2, z3, and z3, z1 terms with a square root on top. So why is this a nice quantity, and why is it more natural than this your 3-point function p3? Well, first of all, we can check that this doesn't depend on the location of the points z1, z2, and z3. And this computation is essentially going to follow from the conformal covariance of the Pn function. The second reason why, and more important reason why this is the right quantity, is that this is conjecturally universal. So we talked about critical percolation on the triangle lattice, but we could have done it on the square lattice instead, right? And then, if you did it on the square lattice, you'd get a different notion of Pn, but you should get the same ratio over here. Okay. And you can also modify your model in other microscopic ways, like we say that a point lies in a cluster if it lies within 10 delta of the cluster. With that kind of definition, that choice matters when you define Pn, but not in this ratio. And intuitively, the reason for that is because Z1 appears twice in the denominator with the square root, so it like appears once and cancels. That's a very crude explanation, but that's roughly why. One other thing to note is this choice of renormalization factor, which we use to define Pn. This is going to disappear in the ratio as well. Right? In your numerator, you would have this pi I delta to a minus 3 power, and the denominator is minus 6 with the square root, so it also vanishes. So, yeah.
Does it depend on C1, C2, C3? Why isn't it just 1? If I said C1 equals C2, then it looks like it would cancel.
You're completely right, but let me rephrase. It should not depend on these 3 points if they're distinct. Yeah. Are there any other questions? Okay. So this, the conjecture that arose in the physics literature in 2010 is that this 3-point connectivity function for percolation should precisely be one of these imaginary DOZZ formulas with a square root to 3 factor. And the 3 values, alpha 1, alpha 2, alpha 3, are all going to be just the same value, and written in terms of the quantity b, which is 2 over square root of 6. Numerically, this constant is going to come out to 1.022 dot 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 dot. Okay, so this is a fundamental constant in the study of percolation, and it somehow is connected to CFT via this conjecture. Okay, so I'm not going to discuss the proof of this result during the 4 lectures, but Baojin Wu, who is speaking on Friday, will be discussing this Delfino-Vitti conjecture. Okay, are there any questions? Okay. Yeah.
Does this extend to FK percolation?
The short answer is yes, if you assume the scaling limit results necessary. So I think the answer is yes, but I will need to check all of the inputs. But yeah, so the scaling limit result wouldn't exist. And this one critically depends on the convergence to SLE6 of critical percolation.
And also, I think, on the independence in percolation.
Independence.
So I think Federico was working on that, but I don't know if it's gonna for the convergence result. Then your techniques are, if you assume the convergence result.
Yeah, I think we get it. Maybe, yeah. Yeah, I would need to check, but I think so. Yeah, the same statement would be true for Ising. I think you need some further thing, like the convergence of the green function somehow. Like this. Something like you sample 3 points, the limiting. You need some kind of input along these lines, where you take a natural measure on the set of the percolation cluster, and you send delta to 0, and then this limit should agree in law with the CLE cluster measure. You need this kind of convergence statement as well. Yeah, I think this is a bit stronger than what I said earlier. Okay. Okay, so so we talked about 2 possible applications, links between SLE and CFT. The first was this nesting function for CLE. This is maybe more interesting from the CFT perspective, because you get an imaginary DOZZ for a continuous range of parameters, linking these loop models to CFT. The second result is maybe more interesting from the probability perspective, because everyone loves critical percolation. Okay. I guess I have 10 minutes more. Okay, in that time, maybe I'll try and introduce the Gaussian free field and Gaussian multiplicative chaos, and then after this lecture, in the next lecture, we'll introduce Liouville quantum gravity. Okay, so the Gaussian free field, what is that? It's a random generalized function, let's say on the unit disk, which I'll draw here. I actually don't know why I drew that, but okay. So you can define this Dirichlet inner product on the space of smooth functions on the unit disk with, let's say they're smooth up to the boundary of the disk. What you do is you simply take the gradient of the function f, dot product with the gradient of the function g, and integrate over the entire disk. So this gives you the Dirichlet inner product on the function space of smooth functions on the closed disk. Now we're going to consider the space of functions with finite Dirichlet energy, so the dot product of f with itself is finite, and these functions will further specify they have mean zero on the unit circle. Okay, so this is a fairly nice function space comprising the smooth functions, and it's a free Hilbert space with this inner product. We just complete the Hilbert space, and that gives us a new space HD. Now what we're going to do is take an orthonormal basis of this function space, f1, f2, and we're going to sample a countable collection of standard Gaussians, A1, A2, and take this random sum. Okay, so these FIs, these are deterministic, we just chose some arbitrary basis, and the AIs are random, independent standard Gaussians. So this gives us an infinite sum, even though each Fi is a smooth function, the limiting object is not smooth, it's not even a function. It exists in the space of distributions, or more strongly in some negative Sobolev space, which is any negative index. And this random generalized function is, we call it the Gaussian free field. More specifically, we call it the free boundary Gaussian free field, which means zero on the unit circle. Okay, so you can define this object, and this is one concrete way to do it. A different way to do this is just, it's a Gaussian process, so it's well defined once you specify the mean and covariance. So we're going to ask it to be mean zero, and the covariance function is going to be what is stated up there. So the covariance of h, g, and hw is going to be like negative the log of the distance between the 2 points, plus something else which is well behaved away from the boundary. Okay, so for this first term, which diverges when w gets equal to z, we've got the second term that stays bounded if the points are inside the disk and not on the boundary. So if you don't like the previous description, we have this explicit covariance function. So h is a distribution or generalized function. You cannot actually evaluate it pointwise. H of z does not exist as a real number, right? And you can see that because the variance of h of z is going to be infinity. If you put w is equal to z in the covariance kernel, then this first term is just going to be infinite. So you cannot define h pointwise, but you can define the integrals of h against smooth compactly supported test functions, or more generally against anything that's sufficiently smooth. Okay, so we're not really going to require too much the exact covariance kernel or anything. Maybe we talk about a simulation instead. So on the left we have this discrete Gaussian free field simulation. You take, this is a continuous GFF, this is discrete. And the way that is graphed here is the color at each point represents how large your free field is at that point. So in these red regions, the field is taking very large positive values. And these blue regions, your field is taking very large negative values. Okay, and it's discretized, so you actually have a value you can evaluate. On the right-hand side is a different way to make sense of the Gaussian free field. You're going to integrate for each point z. You're going to convolve with a smooth compactly supported test function. So this is an approximation of the free field. Right? You can choose these bump functions to be closer and closer to the Dirac delta, and this becomes this will converge to a free field. You can see this graph is a very, it's It's a very rough process. Okay. Are there any questions about the Gaussian free field? Yeah.
So what would be the zero boundary in the Gaussian field?
Should I put
In your previous slide, you said the Gaussian field was defined as free boundary.
Yes.
What would the zero boundary be?
That's a good question. So, on the one hand, on the slide, if you change it from free boundary to zero boundary, you just specify the smooth function doesn't have mean zero on the unit disk, but it's compactly supported in the unit disk. So the boundary values are the zero for all of these functions.
The function is I?
Yeah, that's right. Yeah. So on the slide, you replace the mean zero boundary with the zero boundary. On this slide, instead, you change the second term in the covariance kernel. So you still get this logarithmically diverging behavior when W approaches Z, but the smooth function is a different smooth function, which vanishes at the boundary. The combination vanishes at the boundary. Yeah. Okay, so yeah, so you can define the zero boundary GFF, but for talk, you just need the free boundary one. Okay. So you can define these approximations to the field if you integrate against this perfectly smooth function. It turns out that if you just average your field, your Gaussian field H on the circles of radius epsilon, that is smooth enough. You can actually define this process. So some notation, we're going to write H with the subscript epsilon of Z to denote the average of H on the circle around Z of radius epsilon. Okay. So with this notation, we say that this is a Gaussian free field with average 0 on the unit circle, and that can be replaced as the thing H1, 0, 0. Okay. So, okay, I've got 2 minutes. Should I can try and finish this and we can call it from here. Yeah. So, I'm going to do a quick computation for the variance. So we're going to compute the variance of this circle average regularization of the free field. So this is going to be like taking the average on the circle of radius epsilon around the point. Okay, so the variance of h epsilon z is we're going to take the integral of h on the circle of radius epsilon around the point z, and we square that integral and take the expected value. When you square the integral, you can just write it as this double integral instead, dx dy. And now we're just going to move the expectation inside. And this one is specified by the covariance kernel up there. Okay, so I kept the term that we care about because x and y are close together. This term blows up. The other term stays bounded. And this quantity, log is a log of absolute value is a harmonic function. So by the circle average property of harmonic functions, if you fix x and integrate out y, you might as well just replace y with the center of the circle z. finally, this quantity is just epsilon, right? Because x is on the circle of radius epsilon, so this is going to be like this. Okay, so the covariance of this circle average regularization of the free field is like the negative log of the regularization radius. Yeah. Maybe we can pick up again after the break.